Good morning, everyone. We'll get started this morning back in chapter 8. Hope you're having a great week. It's nice that it's actually light out in the morning to walk in this week. Hope you enjoyed that. I thought I'd mention, in case you didn't notice, next Monday is going to be freezing. So it's going to be really cold on Monday and Tuesday next week. So I don't know if you guys know where your winter coats are, but might want to dig them out. I'm not even sure where mine is. But anyways, let's talk about, actually I had a couple slides up. I thought I was through all the slides, but there are some octet rule exceptions to point out. Most of these we've already talked about in the case of like SF4. Some structures in the third row and beyond will have a central atom that expands the octet of the central atom. And we've even seen some cases like BF3, we saw a Lewis structure of it earlier where it was deficient of an octet and that was okay within its best Lewis structure. So we'll take a second look at that to see that some Lewis structures will exist that have less than an octet. But then we also might want to take a look at a couple of diatomic molecules that we haven't considered yet in terms of how would we come up with the Lewis structure for things like OH, NO, or CLO. These would be molecules without a charge. So if I'm counting up the valence count for like the hydroxyl, this would be actually what we call a radical. It would be 6 plus 1 for just 7 total valence electrons for that OH radical. Now OH minus, we might consider adding the minus charge first and say, well, what would the charge of the ion be if we add that extra electron? Because at least that gives us an even count. So that'd be 6 plus 1 for that charge for 8. And that would give us a very simple single bond to hydrogen, lone pairs all the way around. And then to come up with the radicals Lewis structure, we just think, well, which electron do we kick out of the structure? Do I want to kick out one of the bonding pair electrons? Probably not. Probably doesn't make sense to kick out a bonding pair electron. But what if I remove one of these electrons from the oxygen atom, doesn't matter which one, and end up with the Lewis structure that simply has one fewer electron. So let's just draw a dot on this face here. And so then that oxygen atom would be deficient of an octet, and there's really no way around that when we have an odd count. If there's an odd electron count for the molecule, there's just no way we're going to be able to satisfy the octet rule for both atoms. So oxygen here would only have a total of 1, 2, 3, 4, 5, 6, 7 electrons. If we think of the formal charge of the oxygen, it happens to be 0. So we should have 6 electrons for neutral charge. That's precisely how many electrons on average if we break the bond in half are closest to oxygen, so net neutral for both of the atoms. And so that's a good Lewis structure for hydroxyl radical, just kicking an electron off the oxygen. Then when I'm thinking of NO, I might start with NO minus. So start with NO with a negative charge. So the valence count would be 5 for nitrogen, 6 for oxygen, plus that extra electron for the charge. And then once we get the structure for NO minus, and we previously did the Lewis structure for NO with a negative charge, we ended up with this Lewis structure here, if you recall, because for diatomics, we're just trying to satisfy the octet rule for both atoms. So NO minus, we can do this, we can satisfy the octet rule, but now when it comes time to kicking an electron off to figure out, do I kick an electron off of nitrogen or oxygen, we have choices, and we might want to try to figure out which one we want to choose. So if I'm going to kick an electron off of one of the positions, I can kick the electron off of nitrogen, or I can kick the electron off the oxygen atom. And so that would lead to these two structures here. So now which one of these is better? So one where I have oxygen deficient of the octet or nitrogen deficient of the octet. Well, the best way to actually choose the better structure is to compare their formal charges. So let's take a look at the formal charge for the structure here. So I'd have a 0 formal charge for nitrogen, and then also for oxygen, I would have a 0 formal charge. Nitrogen would be 5 minus 5 electrons closest to it, and oxygen 6 minus 6. And so that seems to be relatively good. We generally want to minimize formal charges. And so then if I look at the other structure, nitrogen goes negative, 5 minus 6 for a minus 1, and then oxygen should have 6 and it only has 5. So we have a negative and a plus in the case of the second structure. Now that's bad for 2 reasons. One, it maximizes formal charges instead of minimizing the magnitudes of formal charge, but then also it's putting the formal charge kind of on the wrong atom. Like nitrogen's less electronegative, once electrons less than oxygen, so it doesn't make good sense that this would be the best Lewis structure, and so this would be our better Lewis structure for NO. Now, CLO is kind of tricky too in a way, but we might want to start it in the same kind of fashion. Start with CLO minus, so 7 for chlorine, 6 plus 1 for the charge, so 6 for oxygen plus 1 for the negative charge, 14 total electrons. So that should just be a single bond. And so we arrive at this Lewis structure. And again, it's kind of like the NO example where we can either remove one electron to go to ClO, so remove one from the O, or we can remove one from the chlorine. So leave all 6 lone pairs on oxygen and have chlorine then deficient of an octet and try to decide between these two here, which one's better. And again, if we look at formal charges, in the top, chlorine should have 7 electrons closest to it, and that's exactly how many it has, so that's neutral. And then oxygen should have 6 electrons for a neutral charge. It has 6 electrons, so that's neutral as well. ClO, so we've gone from ClO minus to ClO kicking the electron off, so ClO should be neutral in charge. So the top structure is 0 formal charges. Now the bottom structure, in a way, you may think is better because it puts a negative charge on O, so oxygen should have 6, now has 7. Chlorine should have 7, now has 6. So if you're counting the electrons for chlorine, it'd be 1, 2, 3, 4, 5, 6. And it should have 7 for a neutral charge. So it's one deficient of a charge that would make it neutral. So therefore, it's a positive 1 charge. And so if chlorine's positive and oxygen's negative, you may think that's better because oxygen is more electronegative. But when we're given the option between 2 Lewis structures where all else is equal, where one atom's breaking the octet rule, the other's not, in either of the structures, we want to choose the structure that minimizes magnitudes of formal charge when that's possible. So we're actually going to choose this structure here. So it's about minimizing magnitudes of formal charge. We'll see on the next slide, there's a couple examples too where we're going to use that as kind of a way to help us choose which Lewis structure is best by trying to figure out which Lewis structure puts the lowest overall magnitudes of charge. Then if we have the choice, if we can't possibly minimize all the charges onto 0, then we want to try, if we can, to put the more negative charge in the more electronegative atom if given the choice. Now, before we look at a couple more examples that look at the sort of formal charges and compare those, let's look back at BF3 and look at an analog to it, BEF2. So BF3, if you remember, had 24 total electrons. So we had the central boron, 3 fluorine lone pairs around each of the F's. And so that was all of our 24 electrons. So we had no electron pairs left over for boron to have a lone pair. So we don't want to put a lone pair on boron. We don't want to be like, the octet rule is so important, we add electrons that don't exist for the molecule onto the central atom. So if we do this, the problem would be that's too many electrons. That would put 26 electrons in the structure. We only have 24. So we only put electrons on the central atom if we had electrons left over when we count our electrons compared to the valence count. So we don't have electrons left over for boron. We also don't want to make double bonds because that's maximizing formal charges. If we try to make a double bond, we did this before, we're putting a negative charge on boron, a positive charge on fluorine. I'll draw the structure real quick just to make sure you see what I mean here. If we want to try to do this just to try to satisfy the octet of boron, boron's formal charge now becomes negative. It only has 3 valence electrons, so it only needs 3 to be neutral, and so it has 4 now. So therefore it's positive, or excuse me, therefore it's negative, and then fluorine becomes positive. Fluorine doesn't want to give electrons back to boron. It actually wants to take the bonding pair electrons away from boron. So fluorine's actually doing the opposite with boron. It's trying to pull the electron pairs off of the boron atom based on the differences in electronegativity. And the true fluorine atom in BF3 would be partially negatively charged as an effect of trying to pull those electron pairs off of boron. And boron should be positive because it's the less electronegative atom. BEF2 does exactly the same thing, and it's okay that the central atom here in the molecule BEF3 is deficient of an octet. BEF2 is very much the same way. Beryllium only has 2 valence electrons plus 2 times 7, so that's just 16 total valence electrons. So we end up with a structure like this. And then again, the fluorines are trying to pull electrons away from boron. Boron becomes partial positive. The fluorines become partial negative. And if you were to compare beryllium to magnesium, the difference between beryllium and magnesium is magnesium's more metallic and just goes ahead and adopts that 2+ charge. So if we compare this to magnesium, well, fluorine's just taking the electron going to F-, and BEF2 is just somewhere in between. And so BEF2 is somewhere in between where the beryllium has a positive charge. but probably not fully 2 plus. But the key is that we don't need to worry about satisfying the octet rule for every atom. We just try to follow those Lewis structure rules of find the central atom, count up the electrons, single bond first, lone pairs in the non-central, and then compare formal charges. If they're already 0, we're good. So we want 0 formal charges. So the formal charges are 0 before we consider electronegativity differences in BeF2. So that's why we would stop at that particular Lewis structure and not go crazy with double bonds. And then sometimes we might add double bonds to reduce formal charges to expand octets. Like we did that for like SO, I think it was PO4 3 minus. We saw an example, but then we were saying, well, probably the central atom doesn't really do that. So expanding octets is only possible within the 3rd row and beyond, and even then, it's kind of a tricky issue. So you'll see some exam questions that ask, give us a Lewis structure for some ions that satisfy the octet rule, some that satisfy the formal charge rule in the cases of ions like phosphate, sulfate, chlorate, things of that nature. Okay, let's look at a couple more examples here. Let's actually think of a simpler example before we do NCS. And it kind of just goes back to CO2, and there's something I wanted to point out here where for CO2, we had one of the ways we started the Lewis structure was just kind of like this, and we had oxygen on either side like this, if you recall. So some Lewis structures are perfectly fine to connect the dots this way, and this is okay. I think it's doable for things like CO2, for O2, N2, Cl2, F2, for simple molecules. When you start getting into more complicated molecules, that's when we kind of revert and think, okay, we should probably start counting electrons, distributing single bonds, distributing lone pairs, counting electrons, et cetera. But for CO2, there is an example in the book where they say, well, why don't we, like, what's the difference between CO2 being double the way we would have sketched it initially, or the way we did sketch it initially, and then why would this be bad? If we go to this Lewis structure here, if you notice this particular Lewis structure with a triple bond and a single bond has the same total number of electrons. So if we count the electrons for CO2, it should have 4 plus 2 times 6. So it should have 16 total electrons within the Lewis structure. And with the triple bond here, we would still have 2, 4, 6, 8, wrong pointer, 2, 4, 6, 8, 10, 12, 14, 16 electrons. So what makes this structure bad, of course, is the formal charge problem. So what makes the triple bond, single bond Lewis structure bad is that we now have a formal charge on this oxygen here. If I break the triple bond in half, I have 3 closest to carbon, 3 to oxygen. So I have only 5 electrons closest to oxygen, should have 6. So that puts a positive charge on oxygen, and the oxygen over here should have 6. Now it has 7 and goes negative. And so it's maximizing formal charges when we could have kept them minimal over here at, of course, 0 for carbon on both structures, but then 0 for oxygen for 6 minus 6. So another thought for CO2 is that we wouldn't adopt the kind of sillier triple bond Lewis structure because it maximizes formal charges. So I just wanted us to see that if we were considering these two Lewis structures, we're going with, of course, the one we went with from the start, the structure that minimizes magnitudes of formal charge. And so now when you're given a Lewis structure, if we said on a test, which of these Lewis structures below is best for NCS minus, and you're trying to choose between them, your options on a test would be a couple options. One would be, well, just try to do the Lewis structure from scratch. You know, just try to assemble what you would think following the rules of our Lewis structures would be, and try to get to the Lewis structure that matches the choices and try to choose the one that's best. Another option could be, well, look at the choices that are available and try to see if any of them are wrong. A lot of test questions might say which Lewis structure is best for some molecule or ion, and some of the structures may have like an incorrect electron count shown. So one of the things you could do is just say, well, on a test, we could take the electron count we should have within the structure, 5 for nitrogen, 4 for carbon, sulfurs and oxygens group, so 6, add 1 for the negative charge. And so that should be 16 total valence electrons shown. I think all these structures here, let me double check, 2, 4, 6, 8, 10, 12, 14, 16. So these all have 16 valence electrons. So I can't rule any of these structures out just because they have the wrong electron counts. But if one of them like threw an electron pair on carbon or something, we could rule that structure out very easily just by having the wrong electron count. Another thing that we can do, I can see my screen is frozen up again. Another thing we can do is compare the magnitudes of formal charge. And so you can see the first structure has a -2 on nitrogen. The -2 should have 5 electrons. For nitrogen, it has 7, so that's where we get -2. Sulfur is +1 because it should have 6. Now it has 5 electrons. I'm going to draw this even though I'm pretty sure it's not going to show up, or it will in a minute. But the sulfur should have 6, it only has 5, so it's positive. The structure in the middle puts a negative charge on nitrogen, a 0 on carbon, a 0 on sulfur. Nitrogen should have 5, now has 6. And then the final structure, the one with the triple bond between C and N, well, that has 0 and 0 formal charges on carbon and nitrogen. If you notice, all 4 of the structures have carbon with 4 electrons. So carbon's 0 in all of the structures, but then the -1 charge is on sulfur. So the question might be for the better Lewis structure, if I'm choosing, probably ruling out the one with the -2 and the +1 right off the bat because it has the highest magnitudes of formal charge. The 2 lowest formal charges are on these 2 Lewis structures here. And which one of those 2 do you think is better? Do I want to put the negative charge on N or the negative charge on S? Well, which one's more electronegative? Now, again, that's a tricky question, but the 4 most electronegative elements, sometimes it's useful to remember it's NO and F and Cl. And then in order, it'd be fluorine's the most, oxygen's the next, NL and Cl have the same electronegativities. And so that's how we can know that we are going to want to put that negative charge on nitrogen. So we'll go with the structure in the middle as the best Lewis structure. Now, we could have assembled this structure from scratch too. We could have approached this problem and said, well, why don't we just build this Lewis structure from our Lewis structure rules? So let's take a look at that real quick. I really don't know what it is that makes this freeze up like this. Okay, so what if we were trying to assemble a Lewis structure for NCS just following the rules? Could we have gotten to these structures by taking the central carbon, starting with sulfur and nitrogen on either side? Our Lewis structure rules are to start with lone pairs, and then consider if we have the proper number of electrons shown, and we do, that's 16, that's all 16 available electrons, so there's no lone pairs for carbon. And then my formal charge right now on carbon's 2+, should have 4, only has 2, so we have a charge, and we have the ability to pull electron pairs in. It just becomes a question of, well, where do we pull the electrons in from? And so if we pull one of the pairs in from nitrogen, then that drops nitrogen's charge from -2 now down to -1. And then sulfur still at its -1. So then for the sulfur atom, we pull in another lone pair to go to double, dropping this now down to 0 for carbon. It was +1 in the meantime. When I made the first double bond, it dropped to +1, but now it's all the way down to 0. And then sulfur's formal charge here is at 0, nitrogen's at -1. So I think I can get to this Lewis structure just by applying my Lewis structure rules, just by starting with single bonds, lone pairs, and then pulling in double bonds as there's charge and availability or room around that carbon to pull in charge. And then I don't do another one, like I don't pull this pair in here to drop this to 0 because that would make carbon -1, and so that wouldn't make any sense. So I don't make like a 5th bond to carbon. In fact, carbon will form 4 bonds, and almost every Lewis structure you ever find involving carbon, it will have 4 bonds. If you have 5 bonds to carbon, probably made a mistake somewhere. Oxygen likes to form 2 bonds or 2 lone pairs, or 1 bond and 3 lone pairs. Likes to either have a charge of 0 or -1. You could pick up some trends that we'll see as we get into chapter 9 for things like C, N, O, for the types of bonds that they like to form. Nitrogen likes to form 3 bonds, either through a triple bond in a lone pair or through 3 single bonds in a lone pair. So there's some patterns that we'll pick up. You'll see a lot of those as you get into OChem 2 later. If we do the same kind of example for the molecule N2O, where nitrogen is the central atom, we have the same kind of basic comparison structures where we can do triple single, single triple, or double double. And so the question is, well, which one of those structures is better? If you look at all of these structures here, nitrogen in each of them has 4 electrons for the central atom. So the central atom isn't changing in its charge. The central atom is actually always positive here. And so the central atom's not changing. What's changing are the formal charges of the outer atoms. And so the first structure here has a 0 formal charge. Nitrogen should have 5, and it has 5. So that's 0 formal charge. Oxygen should has 6, it has 7, so that's a minus formal charge. The structure here, oxygen now goes positive, should have 6, it only has 5. Nitrogen should have 7, or excuse me, nitrogen should have 5 and it has 7, so that's a minus 2. So that seems pretty bad. It seems pretty bad to have a minus 2 on N and a positive on oxygen. And that's also maximizing formal charges. So this one already right at the bat seems like the most wrong structure. And then this structure over here has nitrogen with, should have 5 and it has 6, so that's minus 1 formal charge. And then oxygen here should have 6 and it has 6, so that's 0. So which of these Lewis structures, let's call them A, B, and C, do you think is best for N2O? Who votes for A? Probably most people that would vote for this one, and that is the best because, you know, we're comparing these two. We're really comparing A and C. B is the worst because B is maximizing charges. We can rule B out for sure because it's maximizing the formal charges, not minimizing them. And if I can put a minus 1 and a 0 on N or O, I want the negative on the O and the 0 on the N if given the option. And so the key is, if we can choose to put the negative charge on the more electronegative atom between two Lewis structures that otherwise are the same, then I choose the Lewis structure that puts that negative charge on the O as opposed to the N. Okay, so it's about minimizing magnitudes of formal charge, and when we have options, then we can choose the one that's putting the more negative charge on the more electronegative atom. If you go back to the CLO example previously, where we were comparing two structures that were neutral, and it was positive, negative, that if we can minimize, we do so. So minimize magnitudes of formal charge is your best Lewis structure. And then if you have multiple Lewis structures that have the same minimal charges, then start playing the electronegativity game. And just remember, your electronegativity is fluorine's the highest, then oxygen, then nitrogen, and chlorine are about the same. So that if you're picturing those are your 4 most electronegative atoms, you can know any other atoms less electronegative. Let's take a look at CLO versus BRO. Which molecule has a longer bond length? One little thing you might compare between the two is just their best Lewis structures, and this kind of goes back to, you know, where we were going with this Lewis structure here. For CLO, single bond, BRO would have the same basic Lewis structure. And the difference between these two atoms, they both have single bonds, but the one with the bigger bromine, of course, is going to have the longer bond. So the longer bond would be BRO, and that's just because the size of bromine is bigger than the size of chlorine. So if bromine's bigger, makes it have a bigger bond length when it pairs up with an oxygen atom. Now, which one's more polar? So if we think of charge magnitude, now we need to think differences of electronegativity. And so even though chlorine's more electronegative, it's about its difference compared to O. So O is really electronegative, chlorine's fairly electronegative as well, but bromine's less electronegative. I get a bigger difference of electronegativity between the BR and the O. So I'm going to expect that BRO has the higher charge magnitude, meaning when I'm thinking of oxygen pulling electrons away, going partial negative, partial positive, that it's about the differences of electronegativity. So electronegativity difference is bigger with the less electronegative bromine. So I'm comparing like the electronegativity of oxygen minus electronegativity of bromine, and that's bigger than it is the difference for the two really electronegative atoms, Cl and O. And so the result that should have is it should mean oxygen can pull electrons away from that bigger, less electronegative bromine. So oxygen is going to be like, I'm going to steal those electron pairs even more than I could chlorine. Chlorine's going to put up a bigger fight, and it's going to keep more of its charge and not allow oxygen to go as big a negative charge. So if we're comparing the magnitudes here, the magnitude of negative charge on oxygen should be higher in BRO. Now, dipole moment's kind of interesting. Dipole moment is equal to mu. The dipole moment is equal to charge magnitude times R. So the charge magnitude for BRO should be bigger, and its bond length is bigger, so its dipole moment should, of course, be bigger for BRO. So if you're thinking just the magnitude of the dipole moment we can measure as a property of BRO, we'd expect that to be a bigger value than for CLO because the charge magnitude's bigger and it has a bigger bond length. Now, occasionally we may make a trend between molecules where if they have similar Qs, but one bond length is shorter versus longer, you could sort of see how just having the same charge magnitude but longer will make the dipole moment bigger for a molecule, even though the charge magnitude Q may be the same. Q is really what we mean by polarity. Q is the charge magnitude that's being distributed. This is really what we're looking at in the case of polarity, that the higher the charge magnitude, the higher the polarity. Sometimes that gets a little bit confusing with dipole moment, where it's kind of a measure of polarity, but not a direct measure. It's a measure of polarity and also its relationship between bond length. So the greatest polarity for BRO, because it has the highest charge magnitude, we go with BRO being more polar. It has a bigger dipole moment too. But I guess the point is some molecules, it's possible to have a smaller dipole moment, but yet larger Q magnitude. So it's all about the charge magnitude for polarity, and then this connection back to dipole moment. So I think there's just one more slide from the chapter slides, and that's ranking bond length trends in a couple of molecules of oxygen, hydrogen peroxide, and ozone. I added three pages of additional chapter 8 review problems that we'll look at today too. So right after these, I'll do 3 more problems from chapter 8. Those are in the lecture slides page where you get your notes from. And so let's take a quick look at our Lewis structures here. So we know we have a double bond for O2. And so we have that double bond. Hydrogen peroxide, there's a few ways we can do the Lewis structure. One of the probably easier ways is to kind of just think of oxygen in terms of a dot diagram. Gets us pretty quickly into the hydrogen peroxide structure because we just pair up our dots and we end up making a single bond between oxygen. So we can end up with a single bond between H2O2 just from like a dot diagram perspective, kind of like we put together for water, CH4, O2, N2, et cetera. You could also apply the rules. So you could have said, okay, this molecule here, we know hydrogen can't be a bridging element. Like if in your head, you just know hydrogen's not going to link 2 different O's together. So hydrogen has to be on the outside. So you're probably thinking it should have this base connection here. Whoops, I meant to get an H. So if you're following our Lewis structure rules, you may have just ended at this structure here and then said, okay, I'm going to count my electrons, 1 for each H times 2, 6 times the 2 O's. So that would be a total of 14 electrons. And so far, we've only distributed 6 electrons. So we have 8 electrons left to go. So how about 2, 4, 6, 8? So you can get there from the Lewis structure rules too. It's a little bit peculiar maybe that we have 2 central atoms that we're kind of connecting the dots to within the Lewis structure rules, but you can go Lewis structure rules or just like dot diagram to get to the single bond in hydrogen peroxide. And then lastly for O3, its comparison was, one of the oxygens has to be the central, the other 2 are attached. If you remember, our Lewis structure kind of started like this, and then oxygen has 6, so 6 times 3 is 18 electrons. So far, we've only distributed 16 electrons, leaving 2 behind to go onto oxygen. So oxygen's deficient of an octet. It has a 2+ formal charge. So it should have 6, only has 4 electrons. So we pull in a double bond. So we make a double bond, reduces that charge down to plus. Then we can't make another double bond because oxygen's at its limit for electrons here. We can't expand the octet, so we can't make a second bond. But then we remember that we have this resonance effect. So the resonance effect, if you remember, is that we could have made the double bond over here, had the equivalent Lewis structure, which means the real molecule exists as the average of those 2. So the average structure would look something like this. And it turns out to have a bent bond. So I'm going to draw it bent lone pair up here. And then we have this like extra bond here, where this bond here is like a 3/2 bond. It's like a bond that's not quite double, not quite single. We're sharing the 1, 2, 3, or 1, 2, 3. So we're sharing the 3 bonding pairs of electrons across the 2 covalent bonds. So what we're doing is taking 3 bonding pairs and spreading them across the 2 oxygen-oxygen bonds. So it's not a single bond, it's not a double bond, it's somewhere between single and double. And so now if we're ranking the oxygen-oxygen bonds in increasing length, which of these molecules, if we call the molecules A, B, and C. Which molecule, A, B, or C, do you think has the longest oxygen-oxygen bond? Probably the single bond, right? So we'd expect B, the single bond, to be the longest bond. We'd expect O3 to have a bond length in the middle. And the key for resonance is that one of the bonds in ozone isn't like short and the other one's long. They're both on average about 3/2. So the resonance effect means ozone looks more like this and not like either of those two. They're still good Lewis structures. They still help us get to the resonance picture and an idea of what ozone might look like. It doesn't make them wrong, so I guess I'm crossing them out not because they're wrong, but just because ozone doesn't really look like either one of those two structures. It looks like the average or the composite of those two structures. And so O3 would be in the middle for C, and then O2, molecule A, would be the shortest because it's a double bond. So double bonds are shorter than single. If we had a triple, in one of these cases, a triple bond would be even shorter. So triple bonds are the shortest, then 1.5 bonds, then single bonds. And that's exactly what you get. If you look up their bond lengths, they go with that trend. Before we moved into chapter 9, I thought we should look back at some of the early part of chapter 8 just to get a quick little review here of lattice energy comparisons. So we were comparing lattice energy at the start of chapter 8 to compare our ionic bond strengths. And so when we're looking at plus and minus charges, that if we're exchanging charge, it's better to have the ions small than big. So cesium iodide, now one of the keys is making sure we see that these are both +1, -1 ions, that the difference is really small compact ions will have a greater attractive force, more energy to separate than if you compare to cesium iodide, where cesium's really big and iodide is big as well, that those charges are further away from each other, going to be easier to separate. So it's easier to separate larger ions. So the larger the ions, the lower the lattice energy, and therefore the smaller the ions, the greater the lattice energy. So LIF should have the greater lattice energy compared to CSI, just comparing size. Now this goes by the energy of electrostatic attraction is kappa Q1, Q2 divided by D. So if you have ions that are closer together, their distance together is closer, that gives you a magnitude of attractive force that's greater. So it takes more energy to separate those ions. Same thing with the charge magnitudes. So if you think of the magnitudes of charge, that the higher those magnitudes of charge, then the higher the energy of attractive force, the more energy to separate. So if we're comparing +1, -1 to +2, -2, it's going to take more energy to separate the +2, -2. So LIF and MGS should require more energy to separate. And then remember your lattice energy is the energy associated with the solid ionic compound turning into gaseous ions, where these are gaseous. So it gives you a measure of the ionic bond strength. So the energy of this equation would be equal to the lattice energy. If you think of the opposite of this reaction, if you think of the plus ion of magnesium forming an ionic compound with sulfide, that's really negative. So the opposite of the lattice energy equation is really an exothermic reaction. And so that's showing you that the driving force to form an ionic compound is the association of the ions. So it's the attractive force and nature between the ions that leads to the formation and the stability of ionic compounds. So this slide here is really not one where I want us to see a lot mathematically. Like there are some examples, like I could throw a math problem at this and it's kind of it's a really gory Hess's law problem. I wouldn't worry about preparing for the Hess's law nature problem here, where if I give you all but one of these energies, you can solve for it using Hess's law. I wouldn't worry so much about that part of the process as much as I would just conceptualizing which of these steps is exothermic versus endothermic and kind of why. And so let's start our attention here, because this is our elements. Magnesium naturally occurs as a solid, chlorine naturally occurs as a gas. In their elemental forms. And if magnesium is going to convert into a gas, it has to absorb energy, like solid to gas for any substance. To sublime a substance, in order to go solid to liquid to gas, you have to absorb energy to undergo that transformation. If you want chlorine to break its bond to go to 2 chlorine atoms, that also, all bonds are endothermic, so it takes energy to break bonds, so that's an endothermic step. Ionization energies are all positive, and ionization energies from chapter 7 are all the energies for gaseous atoms. That's why we were converting magnesium solid to gas, so that we can know that the first ionization energy of magnesium, that's a number we might remember seeing back in chapter 7, that's a positive. It takes energy to ionize electrons. Even though we think magnesium 2 plus is more stable than magnesium, it really isn't. It takes energy to create magnesium 2 plus, but it's a question of what you get back as a result. You get back a little bit of the energy and you go downhill. So the only exothermic step so far is putting the electron onto chlorine instead of magnesium. So that goes downhill because that electron's more stable on chlorine. So that's an exothermic step. So our first exothermic step in this process is the electron pair, or the electrons that were lost by magnesium being placed onto chlorine, but that's not enough energy to drive this process to be net exothermic. We then have to associate the ions together. And so the ions being associated together is the other exothermic step. That the association of the ions, the attractive nature of the ions, is what drives then the formation of the compound of MgCl to be more stable than the reactants we started from. So magnesium versus chlorine versus MgCl2, it has all to do with this process here being negative, that the elements of magnesium and chlorine converting into the products MgCl2 is exothermic, and it's exothermic due to the nature of the associative attractive force between the cation magnesium and the chloride ions. Without this value here, this wouldn't have been a process that would have been as exothermic, or maybe even exothermic at all. So if you then compare, this is where the stability of magnesium 2 plus and chloride come from. If you stopped at magnesium and tried to say, well, why not Mg plus Cl minus? Well, you're not going to get back as much energy with the +1 -1. And then, so the energy you have to absorb to lose the second electron on magnesium is small compared to the energy you get back from the +2 -1 interactive force between magnesium and chlorine. You can also think, well, why not magnesium 3 plus? Well, that has a humongous ionization energy. So it would take way too much energy to create the loss of the third electron from magnesium that we never would go there, because you're not going to get enough energy back from the attractive force between magnesium 3 plus and like another chloride ion. So it's all about not just, the noble gas configurations, it's just about how those configurations make magnesium relatively small to give a strong attractive force between the ions, and then they make this number here the most overall negative it can be compared to any other possibility. So noble gas configurations, good moniker to help us understand, or a good way to help understand which ions are more stable than others, but it's really once they form and then they experience their attractive force that allows us to really see why it is that they're so special. So hopefully you can see the relevance of this is just to try to think which steps are exothermic versus endothermic in the formation of ions and then into the formation of ionic compounds. Lastly, I want to introduce this question here, just that we'll see this come up in chapter 9 too, on localized versus delocalized bonding. The bonding in like ozone that we were talking about earlier, this is delocalization. So when I'm taking this double bond that I think is here and I'm changing it to be over here, that process of thinking that ozone forms this like 3/2 bond, that's what we think of and give a word to called delocalization. So I just want to make sure we mention here in chapter 8 that this is delocalization. If we had just a normal double bond that didn't do this, like when I look at formaldehyde in A, that's just where we have 2 hydrogens. And then if we had started here and then had our positive charge here, then we end up making the double bond. We did this Lewis structure before too. So we end up with a C double bond O with 2 pairs of electrons. My screen is playing catch-up games again. But we're gonna end up with the double bond on formaldehyde. And then as our best structure, this is a localized bond. So the double bond in formaldehyde is localized, meaning it's exactly where we think. If a double bond like carbonate's going to have this delocalization, where carbonate, we're picturing the 3 O's, picture lone pairs all the way around. And then calculate the formal charge. From this point forward in the notes today, I am in my office after lecture because I forgot to hit the record button after reconnecting my screen. But anyways, let's calculate our formal charge on carbon. We should have 4 valence electrons on carbon. For a neutral charge, we only have 3, so that's a net charge of +1. So we have a positive formal charge on carbon. All the oxygens should have 6. They have 7 electrons, so these are all minus formal charged oxygens. And so we have a positive charge on carbon. We have room for another electron pair, so let's make a double bond. So we make a double bond, so that reduces carbon now down to 4 minus 4 for 0, for a 0 formal charge. This formal charge is now 0, and then our formal charges are still negative on the outer 2 O's. So then in the case of carbonate, I could have made the double bond here or here as well. So I could make these 2 structures here instead. And so this is a resonance structure then, and then this is another resonance structure, because these are equivalent yet different Lewis structures that represent the same ion of carbonate, just the difference being, well, which double bond do I make? In the real structure, that double bond is going to resonate through the structure. So the real structure of carbonate looks more like the average of the composite of these 3 structures. And so this is why carbonate has 3 equivalent CO bonds that are all of equal length due to this resonance delocalization effect. And so we call this double bond, if we're picturing this double bond, let me do a laser pointer. So this double bond here to here to here resonates across the whole molecule at all times and is delocalized. So this is the best picture for carbonate. It's really not here, here, or here ever. Those are still good Lewis structures, don't get me wrong, but the real picture of carbonate looks like this delocalized structure. So we call this delocalization due to resonance. And so carbonate has a delocalized double bond. OF2 doesn't have a double bond at all. OF2, oxygen, we can do the OF2 structure just from a dot diagram and connect our dots here. We can connect our dots here. And so we can also apply our Lewis structure rule. We previously looked at OF2, so I won't go back through. But you can go back through, count up the electrons, distribute single bonds, put the leftover electrons on O, and see that there's no double bonds here, 0 formal charges all the way around. So OF2 just doesn't have any double bonds, and then CH2O has that double bond. So it has a localized double bond. So a localized versus a delocalized double bond. A localized double bond is exactly where we're writing it here. It's not somehow going into the other 2 bonds and spreading out or resonantly delocalizing itself across other bonds. So it's discretely or exactly precisely where we think it is between carbon and oxygen in CH2O. All right, so let's get a start here in Chapter 9. So Chapter 9 is on molecular geometry and some bonding theories. And we're going to start off with a lot of pictures of Lewis structures and then trying to connect those Lewis structures to some sort of idea of then 3-dimensionally, how does this molecule use space to fill in its molecular geometry. So we'll talk about molecular shapes, the VSEPR model. So VSEPR stands for the valence shell electron pair repulsion theory. And so it just kind of goes into the idea that if you look at something like nitrogen and ammonia, so NH3 has the Lewis structure with 3 hydrogens, the lone pair on nitrogen. So we have these pairs of electrons. Now there's electrons in these bonds, so these have negative particles. This pair of dots here, those are negative particles. Those all repel each other. So the bonding pair and the non-bonding pair electrons repel each other. Well, we call these electron domains. So we call these all some sort of electron domain. We have a non-bonding domain, NB, and we have a bonding domain. And those domains all repel each other. And they're going to be what we need to account for to understand the shape of ammonia. So we'll see its shape in a minute. So we'll talk about molecular shape and polarity. We discussed, or I brought up in Chapter 8, that some molecules will exist with polar bonds, yet somehow become non-polar molecules. So we need to figure out what that's all about. We'll talk about covalent bonding and some orbital overlap theories to get into hybrid orbitals to try to understand multiple bonding and molecules and a picture for what those bonds look like. And then after midterm 2, in terms of coverage on exams, we'll look at some MO theory, molecular orbital theory, second row diatomic molecules to try to understand the bonding in these molecules here. So we'll look at that in terms of coverage for the exam following midterm 4 on to the final exam. Once we get through chapter 9, we then look at chapter 10, 11, and then just part of 12. So we just look at part of chapter 12 to finish up the class, if you're wondering where we're heading after midterm 4. Since I mentioned midterm 4 is not next Tuesday. Next Tuesday is a holiday, Veterans Day. There's no recitations meeting next Tuesday. I can't remember if I mentioned that in this video or not yet, but just so you know, no classes anywhere on Tuesday next week for Veterans Day. You may see in the past we had an activity due whenever we've had holidays during that week, but there's nothing due next week for recitation. So no assignments due next week. I'll post an activity as if we had class so that you can still see what we would have done if we had class, and I'll post a video so you can go over the answers. Okay, let's start today with a picture for CCl4. CCl4, pretty simple Lewis structure. If we're assembling this from the dot structures, we're just taking carbon's dot structure and clicking on 4 chlorine bonds. So chlorine, forming 4 single bonds. Now, the real molecule turns out not to be flat. It turns out not to be a planar structure like it might look here, because these bonding pair domains would all be too close together. So they'd all be 90 degrees relative to each other if it were in this kind of geometry here, and that seems to be worse than another option. So what if those domains just got as far away as they possibly could? So what if our central carbon atom took 2 of the chlorines, put them here in the plane of our page, and then we took the other 2 chlorines and then wedged them in and out of the page into the shape of a tetrahedron. So kind of going into this general shape here of a tetrahedron geometry. And so a central carbon, again, think of 2 of the bonds being in the plane of the page that you're writing, and then 1 coming out and then 1 going back. So this is a way for us to try to sketch structures onto a 2-dimensional piece of paper using these wedges, and hopefully you're seeing this kind of like tetrahedron shape emerge. And the tetrahedron shape, I want to point out, is actually from the fact that this face here has 3 faces. So there are, 4 faces. You get a 4-face tetrahedron structure. It's not exactly because there's 4 things attached to carbon. It was helpful, but not necessary. We'll see an octahedral structure later emerge when we don't actually have 8 things attached. Hopefully we'll make sense of why we call that octahedral later when we get to that topic. But here we see that this structure here, we call this the tetrahedron. We call this the tetrahedral molecular geometry. We often symbolize it just as TD, and that's our molecular geometry. And we also call this the electron domain geometry for this molecule. So it's the domain geometry taken by all of its domains. All the domains happen to be bonding domains, though, for this molecule. Let's then take a look at some other types of possibilities when we have 2 atoms bonded to a central atom or 3 atoms bonded to a central atom. When we have 2 atoms bonded, like in CO2, that turns out to be a linear molecule, whereas SO2 turns out to be a bent molecule, meaning that this bond angle here is less than 180 degrees. This bond angle in CO2 is exactly 180 degrees. And so what's the difference? Well, the difference between the 2 turns out to be sulfur has a lone pair. So sulfur has 3 domains. It has 1, 2, and then 3 total domains that all want to get as far away from each other as possible. So that has to lead to a bent bond. If we tried to straighten out the bond in SO2, then you'd have the interaction of the bonding pair and the non-bonding pair, and they'd repel, and it wouldn't like that geometry, so it doesn't adopt it. When we have 3 things attached to a central atom, now an example that does that is SO3. I like the example here of BF3 a little bit better because we might remember that more precisely as being a molecule that had 3 bonds and no lone pairs on boron. SO3 does more or less the same thing. And so then that adopts this geometry here where these bond angles here turn out to be perfectly 120 degrees. And then the structure is 120 degrees across the board, and we call that trigonal planar. whenever a structure is something planar means all the atoms in the structure exist in the same plane. Now, if you go back to bent, a bent structure is actually planar, but when you have three atoms, if you think about just geometry, there's no way for three atoms to be anything but planar. So linear or planar for the bent. So all these molecules here exist within a single plane as well. So we don't note planar within the bent or linear geometries. It's kind of implied. But now when we have three atoms, we can imagine, well, what if you took a nitrogen atom like an ammonia and you had the lone pair here, and you're either pairing up with hydrogen or fluorine? I'd rather consider this be NH3, but it's the same basic shape as NF3, where you have these bonding pairs repelling the non-bonding pairs. So we take the basic shape of a tetrahedron, and we show this down here, where there's an electron pair in this spot of our tetrahedron, but then for some name, we give a shape name for just where the atoms are, where the atom shape depends on the electron pair. So there is an electron pair here, but they're a lot smaller. There's no nuclear center. So we kind of give a name for just the shape that the atoms take, and we call that a pyramid shape, and then it has a trigonal pyramid. So it's a trigonal pyramid. You can see that kind of here, I hope, where one of the atoms, the nitrogen, is up above the plane of the trigonal hydrogens. And so then if you replace or look at water, they go back to like the structure here. Well, water just has two lone pairs because oxygen has two lone pairs. And so it's taking the basic geometry shape of a tetrahedral structure, but then we're going trigonal pyramidal for our molecular geometry or bent for water, because we're just naming, well, what's the geometry of just the atoms? Even though there's some dependence, like that the water structure depends on there being lone pairs there. So these are all fitting into the tetrahedral electron domain geometry, but then just the tetrahedral geometry versus trigonal pyramidal molecular geometry versus the bent molecular geometry. So you'll see that most molecules will have two different names. They'll have the electron domain geometry and then the molecular geometry. If it's like CCl4, both those geometries are the same. So if you look at CCl4, both of these geometries are tetrahedral. Something I didn't point out on the previous page is that all these bond angles within a perfect tetrahedron are 109.5 degrees precisely. Somebody in geometry and math could probably prove that they had to be perfectly the same at 109.5 degrees, but they're exactly 109.5 degrees, and that puts those bonds further away than if it were square planar. If you remember the previous page, we started off with, would CCl4 want to do this? Well, those chlorines are too close together if they really are planar, so it's not really square planar. Now, one other shape for a AB3 turns out to be a T-shaped geometry. We see this in something like ClF3. Now, why does this shape emerge for ClF3? Well, it's because we have two lone pairs. So we'll have to see why this is the case a little bit later. So we'll get into ClF3 when we look at some geometries of molecules that have 5 total domains. And so the structure here just has 5 total domains. The NF3 has 4 total domains, only 3 for SO3. So what you're doing is you're kind of counting the bonds between atoms as a domain and then the lone pairs as a domain. And hopefully that'll make more sense as we go along. The last thing we'll finish up today with is this slide here. We'll also start with this slide next time, so we won't fully get through all the details of the slide. But what this is getting at is a molecule like CH4 or CCl4 has to have exactly 109.5 degree bond angles the whole way around, because there's no difference in the structure. All those angles are the same. They have to be exactly equal to each other. But as soon as we put a lone pair here, now the lone pair behaves a little bit differently. The lone pair is closer toward the nucleus. It's going to compress the atoms to be a little bit closer together, and it's going to reduce that bond angle. And then it happens even more so in the case of water, and the bond angles are even lower than 109.5 degrees. So we'll talk a little bit about this more next week, but it's because these electron pairs, which again, remember, these are negative particles, but they're going to be closer to the nucleus, so they're going to push the bonding pair electrons closer together. So the bonding pairs don't repel each other as much as the non-bonding pairs repel each other, and as much as the non-bonding pairs repel those bonding pairs. So we can see the geometries here are basically off the shape of a tetrahedron, just with a little bit of adjusting of their bond angles. And we'll get into a little bit more details around that effect into lecture next week. All right, guys, this is our stopping point for today. Have a great weekend, and I'll see you next week.